Hi, my name is Maike Bauer. I'm a first-year PhD student at the newly established Austrian Space Weather Office in Graz. I'm going to give you a brief overview of my poster, which deals with the automated detection and tracking of CMEs using heliospheric imager instruments. I don't really have that many results to present yet, so it's mostly going to be me giving an overview of what I'm planning to do in the future. For a basic introduction, so coronal mass ejections are key drivers of space weather. And if we had an accurate way to predict the arrival of coronal mass ejections, this could help us set up an early warning system, and with enough advanced warning, we might be able to mitigate some of the severe effects that geomagnetic storms could potentially have on Earth. There are a lot of challenges associated with accurately predicting the arrival of coronal mass ejections. I've listed some of them here. One issue is that generally, so some models are able to predict some CMEs with fairly high accuracy, but if you just average it over all CMEs, the prediction errors are generally like in the range of plus minus 10 hours, and you often have very large standard deviations within ensemble models themselves. Other challenges are that the data, so if you want to do real-time forecasting, you have to use real-time data, and the data that is currently available, which is the stereo beacon data that I'm referring to, has a quite low spatial and temporal resolution that's not really comparable to the actual science data that is mostly used for CME tracking. A lot of models also use manual tracks of CMEs as input, so they use time elongation maps that I've also shown on the right-hand side over here. This introduces errors because every forecaster might track the CME a little bit differently. It's time-consuming, and it obviously also requires a human, like a person, to actually sit there and give an alert when a CME is approaching so that it can be tracked. This is what one of these time elongation tracks looks like. This is a JMAP. So what you do is you cut out the middle part of an heliospheric imager observation. So this is the part of the CME that moves in the ecliptic. You stack those cut out parts next to each other, and you then see the CME as this kind of bright streak moving radially outward. This is also then what you track and how you get your time elongation track that you can use as input for your model. I want to very briefly talk about the model that we're using. It's the ELEVO-HIGH model, ellipse evolution based on heliospheric images, which operates on some basic assumptions. It assumes that the CME is an elliptical shape that propagates radially away from the sun. It also incorporates drag-based model fitting, so basically it accounts for the fact that the solar wind can slow down the CME or accelerate it, depending on whether the ambient solar wind is faster than the CME itself. And it also assumes that the CME has a fixed angle of motion as it moves away from the sun. It requires the time elongation profile as input and can predict the arrival time and speed of the CME. So what I want to do in the future is tackle two of these challenges that I've mentioned before. I want to set up a pipeline for automatically detecting, tracking, and then predicting CMEs in real time using these heliospheric imager observations. For that, I think two steps are going to be necessary. I want to enhance the data that is actually available in real time right now until we have higher quality data, hopefully from the VIHREN spacecraft in the future. For that, I want to use generative adversarial neural networks that we've already heard quite a bit about to perform video frame interpolation and upsampling of the low quality beacon data. For the automatic detection and tracking of the CME fronts, I want to use mask CNN algorithm. This is something that I've done like a very basic proof of concept on. You can see like the results over here. This is still a very limited proof of concept, as I've said, because the data set that I used to train this model was extremely small, and this is not publication quality stuff. But basically, this is what I hope to achieve in the future. So you can see over here that the algorithm can kind of mask the region that it has identified as a CME, and that it can do this over a time series. And I hope to do this not only for stereo data in the future, but also for heliospheric imagers on board of other spacecraft like Parker Solar Probe and Solar Orbiter. All of this is done kind of in preparation for the VIHREN mission, since this is all going to be a mission that is stationed as sort of a permanent space weather monitor at the L5 point. And if we had this algorithm that could maybe automatically detect and track the CMEs, it would take away a lot of the effort that is currently associated with having to manually detect and track the CMEs. After we've finished all of this, we also want to investigate if the improved beacon data quality could lead to improved forecasts compared to compared to predictions that use the regular, not improved version of the beacon data. And I guess what I've come here for is mostly to look for discussions and input related to the basic setup of the entire project, since it's still in the very early stages. So if anyone has any input, any comments to this, I'd be more than happy to hear them. And I guess I'm open to questions now.
Thank you so much. Oh, we have a question from Kamen.
Thank you very much. Great plan, by the way. You speak about video frame interpolation. What is the goal? I mean, I know that there's been a lot there have been many papers talking about how estimation of kinematics, for example, is influenced by the cadence. So I suppose you could try to improve those calculations for kinematics.
Right.
But maybe.
So I mean, the goal would basically just be, because the cadence of the science data is like, I think 40 minutes per image, and for the beacon data it's 120 minutes per image. And we also have like frequent data gaps between beacon data, since it's not transmitted continuously as the science data is. So the goal would just be to get beacon data at least on the quality level that the science data is currently at, to hopefully improve the predictions using the beacon data.
Okay. And do you think that could help improve the kinematics estimations?
I think it could. So because we did a study basically showing that the predictions made using beacon data are worse compared to those made using science data. And I'm not necessarily sure if like this is going to lead to an overall improvement in the prediction time. I think we're going to have to work a lot more on the actual models themselves. But I think it might be able to at least improve the predictions that we make using real-time data, which is something that we need if we want to do forecasting in real time.
Great, thank you.
I have a question related to the super resolution part of your slide here. What would be your starting and ending resolutions?
I think right now beacon data has a resolution of, I think, 256 by 256 pixels, and science data is 1024 by 1024 pixels. So I guess this would be kind of the goal.
Okay, and how would you make sure that the upscaled version is still physically accurate, actually?
I guess I don't really have an answer for that as of right now. This is something that I will definitely have to think about when I'm getting to this.
Thanks.
Thank you. We had one more question, I believe. Yes.
So I just want to know, to what distance from the sun will you be able to detect and track CMEs in HI? Because HI images are different than coronagraph images, and you see the intensity going lighter as you go away from the sun.
I think it's up to about 8. I will have to think about this. I think it's up to about 60 degrees of elongation. You're able to see the CME fairly well. I can't say off the top of my head what that is in solar radii. I would have to look that up again. But yes, the fact that they do get fainter as you move outward is a problem as well.
All right, thank you.
Okay, do we have more questions? Thank you so much.